When you were predicting products of especially replacement reactions in first year chem, you probably had to use two charts. One of them was a reactivity series for single replacements, where the rule was that the single element needed to be more reactive than the one it replaced in the compound. So we looked them up on a chart with the most reactive elements being on the top of the chart and the least reactive on the bottom. And sometimes a single replacement might be a no reaction. And it is true, this happens, that the single element needs to be more reactive than the one in the compound. If not, then nothing happens. You know, I can throw pennies in water and nothing happens. Well, copper is less reactive than hydrogen. I throw sodium in water and it explodes because sodium is more reactive than hydrogen. Good news here is you won't have to worry about that. The reactions that they'll give you will work. They're not going to have you do some big fancy problem and at the end be like, ah, sucker, this reaction doesn't even work. So you don't have to worry about that reactivity series. Now, the other chart that you probably referenced was a solubility chart, and we used that one more for double replacements. And the rule with a double replacement was that both reactants needed to be aqueous. And so we'd look them up on this chart and see if they were soluble in water. Well, this one you don't escape. This chart we still need to be familiar with. And in fact, we need to memorize some common solubility rules. Duh, that sucks. I hate memorizing things. I really do. I want to be able to figure it out whenever possible, but there's no better way around solubility. Some of these rules we just have to memorize. Although I think I can make it a little bit less intimidating. You will not be given this chart on the AP test, but yet you will need to know things like, phase symbols. What's the identity of the precipitate? What is the insoluble product and all that good stuff? So here's what I do. I'm not going to try to memorize all these rules, but I will look at the first three. The first three are maybe like the most important, so that's not bad. Number one, nitrates are soluble. It says most nitrates. I'll say all nitrates. Anything with nitrate is aqueous. So when we say soluble, we mean aqueous. It dissolves in water. Anything with an alkali metal or ammonium, soluble in water, aqueous. So any of the group 1, lithium, sodium, potassium, not that we use rubidium or cesium real often, but these guys would all be compounds that are soluble in water, as well as ammonium. So if you had ammonium chloride, ammonium nitrate, or something like that, all ammonium compounds are soluble as well. The other one that I'll remember is this guy, halides. So halogen compounds, chlorides, bromides, iodides, they kind of follow the same trend. They're usually soluble. There are just 3 exceptions: silver, lead, and mercury. Those are the only 3 that don't dissolve. So like copper chloride. Copper chloride, yes. Copper chloride is aqueous. Silver chloride, no. Lead chloride, no. Mercury chloride, no. Anything else with chlorine is a yes. They're soluble in water. So these first 3 are usually the compounds that are soluble without many exceptions. The last 3 seem to have too many exceptions for me. Too many that I don't want to memorize them. For example, like sulfates are usually soluble, but not barium, lead, mercury, and calcium. I don't want to memorize all that. So for example, I may be doing a double replacement. If I see sodium sulfate, I know that's aqueous because I know anything with sodium is aqueous. Oh, so I'll try to remember the first 3 because these are usually the ones that are aqueous. If I do a double replacement and one of the products is a nitrate, anything with nitrate, that's aqueous. Now, if the other product is a sulfate, I bet it's one of these 4. In most double replacements, one of your products is aqueous and one of your products is a solid precipitate. So if you know the common soluble compounds, the other one must be the precipitate. Similar with 5. Most hydroxides don't dissolve real well. The only ones that are highly soluble are sodium and potassium, group 1. The rest of these are either marginally soluble or just precipitates. Like a lot of transition metal hydroxides, like copper hydroxide, iron hydroxide, they're not soluble at all. I mean, they might just be chunky precipitates. I'm not going to try to memorize all that. Or like in number 6, most sulfides, carbonates, chromates, phosphates, blah, blah, blah. Most of them are only slightly soluble or not soluble at all. But I'll know the ones that are. What about like lithium sulfide, sodium carbonate? If I know the compounds that are soluble, then anything else must not be. So if I had like copper carbonate, that's not going to be soluble. I know that the most likely soluble compounds would be lithium, sodium, potassium, cesium, rubidium, or ammonium. So don't get your undies in a bundle trying to memorize all these solubility rules. Think about the first 3. And yeah, you do kind of have to memorize the first 3, but that will usually get you everything you need to know to write a balanced equation. So here's what we probably did in first year chem. They might have said, hey, write the formulas and predict the products, balance the equation for the reaction of solutions, I like that word, of potassium chromate and barium nitrate. Okay, so I need to write some formulas. Potassium chromate plus 1 minus 2. Need 2 of those. And by saying that they're solutions, I know their phase is aqueous. Barium nitrate. Barium and nitrate plus 2 minus 1. I need 2 nitrates, and that is also a solution. Excellent. All right, so you wrote your formulas, and then to do the products, we switch like charges. So you can either switch the positives or switch the negatives. So I could bring maybe barium over with the chromate, and then potassium over with nitrate. And whenever I combine new ions, I check the charges, which is kind of why I like to write the charges, because then I already know them. Or even if I don't write them on the product side, if I wrote them down on the reactant side, I can just quick look them up. Ooh, sweet. Everything's neutral. I like that. So once we wrote the products, we usually balance the equation. Let's see. How about 2 potassiums and 2 nitrates? And how nice. They're right next to each other. And the last thing we usually did was finish the phase symbols on the product side. And we just looked them up on a chart at the time. Now you're not going to have that chart. But look at what happens on the product side. Anything with potassium, anything with nitrate, I have no doubt this is aqueous. And it's real common that in a double replacement, the other product is a precipitate. They're going to do this. They're going to help you out on the AP test. One of the products is usually obvious. It's a gimme. Oh, it's a potassium compound. Oh, it's a nitrate compound. That's the aqueous product. So without memorizing all the barium rules or chromate rules, I could figure out that that's going to be the precipitate. Okay, so hopefully that rings a bell. That's kind of how we wrote reactions in first year chem. That's called a formula equation. It shows all the formulas. It has the equation balance. We put the phase symbols in. But it doesn't really show what's present in the solution. Like, it doesn't really show an accurate account of what particles are present in the beaker. Here's the problem. When we list something as aqueous, it means that it's dissociated. So like when I say a product is potassium nitrate, AQ, there really are not potassium nitrate molecules in the beaker. It would be potassium and nitrate ions if it's aqueous. So now we get a little more particular with our reactions in AP. If they ever ask you for a formula equation, it's just like first year chem. And it's a good place to start. I usually do start by writing a balanced formula equation. But then they might ask you to switch that to a complete ionic equation. In a complete ionic equation, all strong electrolytes are dissociated. If I say something's aqueous, it means that it's really dissociated into ions. By strong electrolytes, we mean soluble ionic compounds, strong acids, and strong bases. Now, weak electrolytes, or anything that's insoluble, meaning it's a solid, or we can think about gases. We could put or gas, something that's gas. If they're not going to dissociate completely in water, then we can just leave it as its formula. Then we're not going to split it apart into ions. So anything solid or gas, or a weak electrolyte. And by weak electrolyte here, we might mean like a weak acid or a weak base. If it doesn't completely ionize, we're not going to split it into its ions. We're going to leave it as a formula. Okay, so let's do this. Down below, let's look at the same equation. So I already wrote the formula equation. Let's see if I can remember it. It was potassium chromate. That was aqueous. Barium nitrate. That was aqueous. We formed barium chromate. That was the precipitate. And I think it was 2 potassium nitrates aqueous. Okay, so now as a complete ionic equation, all strong electrolytes split into ions. Okay, so the only things that I'm looking at are anything labeled aqueous. I'm not going to split that barium chromate precipitate. That's an insoluble product. It's not aqueous. It's not in solution. That's going to stay together for life. The only things that I'm considering are those aqueous solutions. And then I just ask myself, are they strong electrolytes? And the answer in this case is yes. They're all soluble ionic compounds. Yes, we're going to split them into ions. So watch what this looks like. If this guy, this potassium chromate, splits into all its ions, I would have 2 potassium ions. They're +1. They're swimming around in the water. There's going to be a chromate ion, -2. aqueous. Okay. There's going to be a barium ion, +2, aqueous. And there's going to be 2 nitrate ions, -1 in solution. Okay, so you remember like in first year chem when we said that the rule of a double replacement was that both reactants had to be aqueous. In other words, both reactants need to be willing to let go of their partner. If I want to form a new product, I have to be able to switch the ions. If one of those reactants was not aqueous, if one of them was a solid, that means he doesn't want to let go of his partner. If he's not going to let go and form ions so I can switch them around, then there's going to be no reaction. So that's kind of why we said that in a double replacement, your reactants need to be aqueous. They need to let go of their original ion so that I can rearrange them and form new products. That's exactly what happens when these compounds are aqueous or in solution. Or that's why like some reactions, they won't work in solid form because they're not letting go of their partner. They're not letting go of their ion. But if you put them in water, then boom, you form this fabulous reaction. That's really what's present in my 2 original solutions. It's a bunch of ions. So now if I let these guys bump around a little bit, if the barium and chromate bond with each other, That is an insoluble product. We leave that as is. We don't touch that. We don't get to dissociate solids. But I will dissociate the other product. This is really going to look like 2 potassium nitrates. So when each potassium nitrate dissociates, I'm going to have 2 potassium ions plus 1. Those will be aqueous. And oh brother, we need more room. I think I can do that. Whoa. Perfect. We'll have 2 nitrate ions. Aqueous. Does that kind of make sense? Like here, there were 2 nitrate ions bonded together. But if they're dissociated, we can write the 2 out in front and say 2 nitrate ions. They're going to split. Well, here, potassium and nitrate will only split into 1 potassium and 1 nitrate, but I have 2 moles of it. So I'll put the 2 out in front again. And again, everything balances. You know, if I have 2 nitrates on the reactant side, I have to have 2 nitrates on the product side. They're all present, they're just in a little different form. This is called a complete ionic equation, where I've got everything dissociated that's a strong electrolyte. It's written as ions. Oh, I like that. Okay, so now let's switch this back and look at something called a net ionic equation. We already did the complete ionic. The complete ionic shows something called a spectator ion. This term is going to come up a lot throughout the year. Whoever came up with this term is brilliant. Spectator ions are ions that are present, but they don't do anything. They don't chemically react. They don't change in any way. So in a sense, what's the point of writing them in our equation? Because they don't do anything. That's a net ionic equation. It only shows ions that are chemically changed, that are directly involved in the chemical reaction. It does not show spectator ions. When it says ions that would remain aqueous, that's spectators. Spectator ions. They're present, but they're just kind of hanging out, watching the reaction occur. They're not participating in the reaction. So here are my spectators. I'm looking for ions that are the same on both sides of the equation. And let's see if we can add this guy. Whoop, not that one. We want to add this thing. Beautiful. Okay, so I'm looking for things that are the same on both sides. 2 potassium ions. 2 potassium ions. They're exactly the same on both sides. Or here, when I look at the original formula equation, potassium's aqueous. Potassium's aqueous. Those potassium ions don't change in any way. They're spectators, and we can get rid of them. They're not part of the chemical reaction. So we cross them off. I like that. So like in the original formula equation, I usually do start with that. That's how I usually write my original reactions. It's easy to balance that way. It's easy to write the formulas, get all the charges right. But I see that potassium is in 2 aqueous compounds. That tells me that the potassium is going to be an ion on both sides. If potassium is aqueous on both sides, get rid of it. It's not chemically changing. Chromate was aqueous on the original reactant side. Now chromate is part of a solid. That's different. The chromate ion has changed. He's not a spectator. We have to keep him. The barium. Barium started as an aqueous ion, but again, it ends as a precipitate, a solid. Barium ions have changed. We keep them in the equation. But here's the other spectator, nitrate. I have 2 aqueous nitrate ions. And I think I've got 2 aqueous nitrate ions. They're hiding. But I can find them. There they are. Get rid of them. We don't need you. If you're not changing, cross them off. Whoa. So honestly, I write the balanced formula equation first. And then I look from side to side at the phase symbols. If that ion has the same phase symbol on both sides, it's called a spectator. And if it's aqueous on both sides, it's a spectator ion. It's not chemically changing. So really, if I want to scale this down to what's called a net ionic equation, they're usually pretty simple. Let's bring this back. There we go. Here's my net ionic. It only includes the ions that changed. So it's going to be the chromate, starting aqueous. It's going to be the barium, originally aqueous, forming that precipitate. Here's the chemical reaction. Nobody else really changes in any way. Visually, that's kind of what they're trying to show back in this diagram. I like this picture a lot. There are times when they're going to ask you to think about a chemical reaction in terms of a particle model. Or they might ask you to draw a particle model of a chemical reaction. And this is what I'm kind of thinking or picturing in my head. They give us a little key. So these red blobs or whatever, these are my potassium ions. So originally I've got potassium ions swimming in the beaker. I've got nitrate ions that are these little guys, NO3. They're dissociated. They're swimming around individually. I've got barium ions and I've got chromate ions. When I say that those 2 reactants are aqueous, this is what I have to picture in my head. That it's really a bunch of dissociated ions that are free to kind of move around in the water. And again, if one of those reactants wouldn't be aqueous, then I'm not going to have a chemical reaction. They have to be able to let go of each other so I can combine them in new forms. On the product side, here's what I'm picturing. I have that barium chromate precipitate. So that's down at the bottom. Here's my precipitate, my PPT. That's got the purplish barium ions, and it's got these chromate ions. They're supposed to show that it's a solid. They're bonded together. It sinks to the bottom as a precipitate. But the potassium nitrate is aqueous, meaning that it's still ions in solution. They look exactly the same. I mean, check it out. Like, these potassium ions look exactly the same. These nitrate ions look exactly the same. So we may write it in our formula equation because it helps us write the formulas and get it balanced and all that good stuff. But eventually we want to scale it down to a net ionic where we're only showing the ions that have chemically changed. So I write that first. And then if they say, hey, write the net ionic, I'll be like aqueous potassium. Aqueous potassium, you're gone. Chromate aqueous. Ooh, chromate solid. You change. Barium is part of an aqueous reactant, but its product is solid. That's different. Nitrate, you're gone. Aqueous on both sides. So again, here's like my net ionic. The chromate ion, the barium ion, forming that barium chromate solid. A lot of times in AP, they're going to want your equations as net ionics. So start with the formula and then scale it down because it really does give us a better picture of what's accurately present in the beaker.